Slide?
Yes, yes.
Okay. Am I to go now?
Yeah, please. Stage is yours.
Okay. So I'm just going to talk about overview. In fact, this is actually a comparison of most of the current IOL power calculation formulae. Sorry. Oh, okay, this is my financial disclosure. Well, first we're going to look at a single IOL. These are mainly ZCBOO. If you look at most of the publication, they are mainly Equisoft platform. This is 381 eyes. Okay, this is a box plot. What we are interested in are the 4 quartiles. Usually the outliers may be problems due to other than formula, but what we are more interested in, these are all optimized. That means the mean prediction error, which is the actual post-op refraction minus the predicted refraction. The mean of all the eyes should be 0, but we are looking at the quartiles, so the median error, prediction error should be close to 0 unless it is severely skewed. Okay, so you can see here most of the formulas here, the median prediction error is close to 0 except SRK2. The other thing we are more interested in is the compactness of the 2 central quartiles. If this is something like standard deviation, if it's compact, I mean, it is very well, standard deviation is very low. If it's widespread like in SRK2, I mean, it is not very predictable. What we are interested here, you can see is the RBF, Barrett, and EVO is quite outstanding. High gaze is also not too bad. But for this kind of single IOL across all eyes, because most of the eyes are within normal range, you can expect most of the formula to do relatively well. This is the absolute error. Absolute error is a prediction error, but disregarding the sign, whether it's positive or negative, we take them as the same. And then again, this is the box plot. We have the median absolute error, which is something that we are usually interested in. This is also a measure of spread and how far it is from the mean prediction error. The closer the box, the better. Again, here, RBF, Barrett, and EVO. These 3 boxes here is quite good. High gaze ULIP, high gaze personally triple optimized is also very good. This is the percentage error, percentage of prediction error. In the past, we looked at 1 diopters. Today, we should be looking at half a diopter because the formula has improved so much. So what we are looking here, you can see RBF, Barrett, high gaze are over 80%, together with EVO over 80%. The FT1 and FT2 are my own excellent adjusted, published in BJ0208. These are now superseded by most of the newer formula, but it's doing not too bad here. But what is clear is this is time to totally discard SRK2 because it is absolutely hopeless, and don't ever use SRK2 anymore, at least message from here. What about the other data out there, the publication there? This is one publication by Cooke, over 1,000 eyes, compare PCI as well as OLCR eyes for him, and say that the Barrett, high gaze, and T2 do very well here. And for the OLCR, which is the lens star, the Olsen, Barrett, and Olsen do very well here. Plus minus half a diopter is over 80% or close to 80%. Okay. Now, there's other publication by Kane, one by Kane in 2017, and another one by Savini in 2019. For Kane, we found that Barrett was very good here, over 80%. RBF is close to 80%, T2 is close to 80%, Holiday 1 is close to 80%. Savini was using a different strap source biomethods, and he have gotten very good outcome. For him, his EVO, RBF, and Kane were the top 3, hitting 90% with this 3 formula, while Barrett is close to 90%, Barrett and T2. Melles has the most eyes published in 2018, and he has recalculated and some updates in 2019. So we just look at the 2019 For 2019, it's close to 80% of Kane's, Olsen, Barrett, and Evo, and here RBF as well. So you can see it's consistently, these new formulas are doing better than some of the older traditional formulae. The latest is by Cheng. This is just published in, I think, the latest issue of JCRS. For this group, they have very good outcome from Kane, Olsen, Barrett, Evo, and RBF. They're all close to 80%, way above the 70%. This is 410 eyes using strep source OCT. What is interesting from our data is that this is the traditional formula, and this is the newer formula together with Haggis. You can see the traditional formula that's sensitive to axial length. There's a correlate, there's a regression against axial length that's inclined. So if you are long axial length or short axial length, you end up either on under predicted or over predicted. Look at the newer formula and the highest triple optimized, they are neutral to axial length. This is important because otherwise you start to have errors at the extreme of axial length. What about K? This is based on keratometry, the traditional formula. You can see it's again SRKT and Haggis as well. There's Haggis is here, they're sensitive to K. That means the varies with K, their predictability. Hofferkills and Holiday are less sensitive to K. And again, the newer formulae, they are less like Barrett, Evo, and RBF. They are kind of neutral to K. This is corroborated by data from Melles. The newer formulas are less sensitive or neutral to axial length and K, while the traditional formula, some of them are very sensitive to K and axial length. And that is one reason why the older formula, the traditional formula, don't work so well in today's refractive cataract surgery scene. Well, I'm going to look at short eyes. We don't have that many short eyes. It's less than 22 mm, 37 eyes. Here, our data show that from this ZCBOO show that the Hofferkill, Holiday 1, and SRKT tend to end up over predicting with the patient end up with myopia. For this group, RBF is good, Barrett is very good, Evo is also good, Haggis is not so bad. They predict, I said, this is using the same optimized constant from the general population. The percentage of eye within half diopters, RBF, Barrett's, triple optimized or personal triple optimized are all very good. Evo is not too bad. But in our data, surprisingly, Hofferkill and Holiday 1 doesn't do too well. Well, we'll compare with Cooke's eye. Cooke ranked them in his data set. Barrett, T2, and Haggis do very well for PCI, and for OLCR, Olsen, Barrett did very well. So it's slightly different, but there's some consistent formula that do relatively well in most of the data set. Gokce did a study mainly just for short eyes, and we look at the compactness. This is absolute error, the median absolute error, and the compactness for, in his case, Barrett, Haggis, RBF, and Holiday 1 is very good. Olsen doesn't seem to do so well here. This is pre-optimized and this is post-optimized. So it looks about the same. Well, Kane study early on, they also have, look at the short eye segment, and Cheng as well. For these two, they just highlight the better performing formulae. In Kane's case, the Barrett, Holiday 1, RBF is good. In Cheng's case, Hofferkill is doing very well with the new Pearl DGS from Damien Gattinel group is also doing very well. Surprisingly, Kane doesn't do so well, and RBF doesn't perform so well here. What about long eyes? This is 154 eyes. We just look at the long eyes anything that's beyond 26 millimeter. Well, most formulas tend to end up on the hyperopic side. That means the formula under-calculated, giving the calculating the power that is too low, and the patient end up hyperopic. This is using the same population-based optimization. RBF is slightly on the hyperopic side, but it's not too bad. It's quite compact. Barrett is good. I guess it's actually quite good. Evo here is actually very good and more or less in the center. How about within half adapters? Within half adapters, the first four formula, which is RBF, Barrett, Higis, the two Higis stand tall above the rest. Evo is the best performing in this area. We look at the Cooke data set. Cooke data set shows that Olsen, Higis, and T2 is a better performing one for IOL master, and for Landstar, Olsen, and Higis are the better performing, better performing formulae here. Kane's has better performing with a Barrett and Holiday. This is a 2017 paper. The rest of the formulas, Hill, RBF is not too bad. For the really long eye, then the Barrett Universal 2 seems to do the best, followed by Hill RBF. Cheng's the most recent paper shows Kane is the best performing for medium long eye, followed by RBF and Barrett. Actually, all of them perform very well. For longer eye, more than 26, then Barrett, Kane, and Evo performs better than the rest. Now we go to the very extreme. These are the 5 diopters or less, and or the negative territory. I think they're 40 over eyes or 50 over eyes. I can't remember. This is my own data. Of course, you can optimize them for just this segment of the population. And with a conventional formula, you get quite good outcome, but they still end up on the hyperopic side. But to do that, you will have very extreme constants, like in this case, 107, 101. This is not normal, and this is not easily accessible. So what we do is we use what is the A constant on the box, because you can't, these are sometimes different IOLs that they don't have normal power range. And with this, using the constant from the box, you can see here, Barrett and Evo were outstanding. Most of the other formula, these are out of domain, so they won't give you a prediction. So we just work with Barrett and Evo here. And based on ULIP against Barrett and Evos are almost spot on with very tight, very low standard deviation. When we look at plus minus half a diopter, the percentage of eyes, again, this is inaccessible, so let's ignore this. This is based on the box. Manufacturer suggested A constant, and this is based on ULIP. There are only 2 formulas stand out within half a diopters. Only Evo and Barrett are above 70%. The rest of the formula within half a diopters are less than 50%, except for high gauge, which is slightly higher. For Holiday, yeah, high gauge, which is slightly higher. So in this territory, most of the traditional formula does not perform well. You have to go on to the newer formulas such as Barrett or Evo, and hopefully the other formulas will come on board as well. So if you look at all these, the evolutions of a formula, this is the most important slide. This is quite similar to the one published in the editorial by Cooke. When in the past we used 19 diopters, we have a lot of refractive surprises. Then along come ultrasound biometry. And then at that time, we have the simple regression, which is the SRK and SRK2. These are data-driven formulae. Then there's a simple thin length versions formula such as the Bing Horse, the Holiday one, the Hoffer-Q, the SRKT, and then the modified SRKT such as T2, and so on and on. Then optical biometry comes along. Now measurement get more accurate. We can expect better formulas to come along. The second thing is, of course, computational power. In the past, these are all done with pocket calculator. Today, we have computer with processing power that's so good. It takes manually something that takes a week to calculate today. This takes just a matter of mere seconds. So we can have better formulas as well. Holiday tools, okay, and then Highgate, which is mainly based on optical biometry. Of course, subsequently there's ray tracing, iterative thick lens version. These are based on computational power as well as thick lens. They need a computer to iterate the power. And of course, artificial intelligence such as the Hill RBF, and of course, the combinations of optical as well as artificial intelligence. The reality is that the line between all these formulas, all these modern formulas are not distinct because there's quite a bit of overlap between optics as well as artificial intelligence as well. What is clear is a simple regression formula should not be used at all now. And the simple thin lens versions is obviously on its way out. All right, if you have optical biometry, if you don't have the formulas integrated in your biometers, you can go online. You can use the RBF, the EVO, the Barrett, as well as the Kane online. Of course, you can also, some of these formulas are integrated, such as Olsen phaco optics with the topographer or tomographer and the Oculix as well. So with that, thank you very much.